Hi everyone. I'm Abhay, and as usual, we have another new guest with us today. Here is my friend, dear friend actually, Sankalp Sanan. Now, I will give a bit of an intro about Sankalp. Sankalp is currently pursuing his master's in computer science at IIT, Illinois Institute of Technology. He has a bachelor's from SRM. That's a bachelor's in computer science. He has worked on multiple projects on artificial intelligence. He's currently a contributor to the PennyLane repository. PennyLane, again, is a library written in Python for modeling machine learning algorithms in quantum computers. And today, we will be discussing about quantum computing. Hi, Sankalp. Hello, how are you? Thank you
Hi,
very
Abhay.
much for doing this with us.
Yeah, thank you for having
How,
me.
how is how is Chicago? How is Illinois? How is everything going on there?
It's pretty good, I guess. The weather is kind of cold. That's all.
It had been snowing for quite some time there, right? Previously.
Yeah, but the changes in weather are quite drastic. Like one day it's very cold, and the other day it's
It's really hot.
really hot. Yeah.
Yes, yes. So, Sankalp, I know that you are really into quantum computing. You are a co-contributor in PennyLane too. Could you give us a bit of an intro about quantum computing and what is it?
Yeah. So let's see what classical computing is. So
Okay.
basically,
Yeah.
everything the processors designed currently and the processors currently being used in your phones, your laptops, or any devices are basically classical computers. So how they work is they operate on bits, like bits as in either something can be 0 or 1, on or off. So these are the two possible states in a bit of a bit.
Right.
So the classical computers work on these things. So in quantum computing, what a quantum computer works upon, they process in a quantum bit can be in the state of 0 and 1 at the same time. It's not
Okay.
like it's in one of the states, it's in both the states at the same time. So when you combine multiple of these qubits,
Mm-hmm.
you gain a certain exponential advantage when operating on multiple qubits. So for example, if you see, let's take an example of a classical bit and say it's 0, its value
Okay.
is 0. And let's take another classical bit and let's say its value is 1 or something.
Okay.
So when
Mm-hmm.
you add these two bits, you'll get a number, right?
Right.
And so if you want to see all of the all of the possible values you can get using these two bits, there will be four possible values. Once when this bit is 0, and this is 0, then this is 0, and then this is 1, and so on. You'll have
Yeah.
four
Four
possible
different kinds of
answers, four
possibilities.
different
Right.
answers. In order to calculate all these four answers, you'll have to run the addition operation four times,
Right.
because you want to calculate for each state. In a quantum computer, since both of these qubits are in a superposition state, so if a qubit has the value of 0 and 1 at the same time, it's called as a superposition state.
Superpositions.
So if both of these bits are in a superposition state, then once you add them, you'll get all four answers in one operation.
Okay.
So
So
in
that four is condensed to single operation. That means.
yes, so this is the exponential upgrade that you're getting once if you're using a quantum computer. This is a very rudimentary example of how a quantum computer works, but I this is a like I wanted to explain it in simple terms. So this
Yes.
is what it does basically. So you were using four different operations to
Mm-hmm.
get four different answers. In this case, you're only using one operation to get four answers.
Yeah. So instead
That's
of going through the whole thing four times and putting like in that each placeholder would have a single value and then a second placeholder, a second value.
yeah.
Doing that four times, you just have one placeholder, one second holder had two superimposed states.
Yes. Yes.
Summing those up, you'll get all the four states at the same time. That's what you're saying.
Yes.
Right.
So
Okay.
that's a speed up in
That's a speed
compute
up.
time.
Yeah.
Yeah. So that's what a quantum computer does. And yeah, this is what helps this superposition. There are certain concepts in quantum mechanics
Yeah.
which superposition is one of these concepts. There's entanglement, and there's teleportation, quantum
Okay.
teleportation, quantum entanglement. So these three are the basic fundamentals in quantum mechanics, and once you use these to create computers, that's the field of quantum computing.
Quantum computing.
Yeah.
Okay. Right. What led us to quantum computing? Could you tell me a bit about that? We had conventional computers. We were using transistors, and then we came up to making adding these transistors up, making these processors, and now we are in the age of quantum computing. What led us here? Could you tell me about it?
Yeah. So the motivation for quantum computing was in the I so I can speak for the current times.
Mhm.
What Why the quantum computing has been hyped, like
Mhm.
it's being hyped right now. It's one of the reasons is, I don't know if you know about this. It's called Moore's law. So
Okay.
Intel has been using the Moore's law to upgrade their processors
Okay.
for the past 20 years. They've been doing
Okay.
this. So what a Moore's law is, it's a very simple law. It just says that every 2 years, the number of transistors you're using in a certain area will double. So
Okay.
for a certain size, the number of transistors will double in that area.
Hmm.
So every 2 years that'll happen. So as you know that the CPUs are made up of transistors. There are a million
Yeah.
transistors. So but now we are reaching a limit after which we cannot create. So if a transistor, if you're increasing the number of transistors in a particular area, then that means you're decreasing its size. So the transistors are
Okay.
getting smaller and smaller in order to fit the required number of transistors in a
Mhm.
simple in a small area. So once you're if you're using if you're decreasing the size of a single transistor, you will reach a limit where there's this thing called tunneling which
Okay.
happens. So what happens is, there's a blocker between two fields. So electrons it what it does, it prevents electrons from passing from one side to the other side. That's
Okay.
how a transistor stops the electrons from passing. So that's
Okay.
how a transistor creates a space of zero. It creates a state of zero, and
Okay.
if the electron passes, that means it's in a state of one. So
Understood.
if you're decreasing the size of the transistor, you'll reach a point where the electron will pass through the blocker anyways.
Oh, there is no stopping that.
Yeah,
It will
it won't.
pass. Okay. It won't
Yes,
stop. It will pass without resistance. That means.
it will pass without resistance. So
Mhm.
this is called tunneling. The electron will just pass to the next state. The blocker
Understood.
won't be
Yeah.
able to block it. So because the size of the transistors are so small. So currently, what Intel is using is a 14 nanometer architecture. So each transistor is of the size of 14 nanometers.
Okay.
Then AMD recently came up. I think it's been 3 to 4 years since AMD came up with 7 nanometer architecture. This is the
Okay.
reason why AMD has been such a driving force. Like AMD has been so much popular in the recent years because they were able to come up with their Ryzen processors, which use a 7 nanometer architecture.
Okay.
So if you're reaching this limit, that means your transistors are not you won't be able to build CPUs using transistors. If you're
Okay.
This is the end of Moore's law. This is the point where quantum computers come in.